First of all, the difference between linear and non-linear, and indeed p-delta analysis. So here we have a cantilever. It has an axial load and a point load, and these are just unit values, and the cantilever is 1 meter long. So, okay, a trivial problem to work out by hand. You know the axial load is going to be 1, the bending moment is going to be half, the shear force 1, and so on. And if indeed we run a linear analysis and look at the results, that's indeed what we get, as you'd generally expect. A bit of deflection. Now, we can also run a p-delta analysis on this, because obviously as the cantilever bends over, this axial load should start to induce bending moments on here. So let's do a static p-delta analysis. Add in our loads, just the one load case, and analyze this. And if we just add in the bending moments, so you see, for the p-delta analysis, the bending moments are pretty much the same still. And again, likewise, if we do another, say, non-linear static analysis on this little cantilever, and don't magnify. We can see the bending moments and so on are very similar. If I go and open up the output, let me just reduce that down a bit, so just remove the interesting points from the results. So we're just seeing the end value. So see, case 1 is the linear, 2 p-delta, 3 is the non-linear, and you can see the axial load is reducing fractionally, and the moment, if I use the highlighter, the moment is fractionally increased. Not a big difference, but then again, non-linear is, obviously linear analysis is suitable for small deflections, and that's exactly what we're getting at the moment. If I go and add in that, you'll see that the deflections are tiny. So let's delete those results, leave the analysis cases there, and I'm going to increase these loads by a factor of 10. Okay, let's rerun the analysis. Now, the load is now 10 times the size, and you'll see that, let's look at the axial load. Actually, let me just do that. Right, the axial loads, sorry, what am I getting there? By case. Right. Yes. The deflections, you see, are getting slightly larger with the non-linear and p-delta. And if we look at the axial loads and the bending moments, you see the axial load is slightly getting smaller, and the bending moment is increasing slightly. Now again, they're still very similar. But now, if we again multiply these by 10, so the loads are now getting quite significant for this small cantilever. And run these results again. We can see that now, looking at the deflections for the static linear analysis is getting large now, and they're diverging hugely from the p delta and non-linear. This is now a large displacement problem, and linear analysis just isn't working. Likewise, if I scroll down and we look at the say the axial force, now you notice the axial force is the same for the p delta and the linear, but for the non-linear, axial force is greatly reduced. But on the other hand, the moment is much larger than the static. So if we just go over to the graphical view, we get a good idea of what's going on. Now this is deformation magnification of 1. So this is actual deformation, and you can see why we're getting increased moments, and also of course likewise the axial load is reduced because of the whole thing is shifting. The whole is very much a different problem to how we started. So linear analysis can be good for small deflections, but once you get large deflections in your model, non-linear is the is required. Now, apart from so there's that aspect of non-linear. We can also use non-linear elements. Now, non-linear elements are strut and tie elements, so compression only and tension only elements. So we have a simple portal frame with beams around the outside and some cross bracing. Now I've used stage analyses on this so that the first analysis case we've just got bar elements, so bars are axial only, carry tension and compression. Oops, missed. Oh. Okay. We've also got strut case where we've got compression only elements and tie only. So let's run these three static analyses. These are linear analyses but with non-linear elements. And let's look at the results. So if I switch on the axial load readout, and we can see the axial load when it's bars are both the same in both directions, and we're getting a certain amount of bending moments. If we go to the strut model, we can see we're getting a much higher compression load in this strut, nothing in the other direction. So it's carrying the compression load from this point load at the top. I forgot to show that, sorry. That'll make more sense. And likewise, if we turn these into tie elements, again, this element carrying all the loads, the other member carrying nothing at all. And the deflection slightly larger as well. Now, because these are non-linear elements, in a linear analysis, what will happen is GSA will check to see whether they are, so let's say they're using struts, and if the strut goes into tension, GSA will switch them off and then rerun the analysis, and then see how the results go from there. Now, someone's got their hand up. Okay. Let's check. Well, if you want to, if you've deliberately put your hand up, can you put a question in to us? That's Will. Okay, no worries. All right, I shall press on. Alright, so that's non-linear elements, but the linear analysis, and because these are non-linear, you can't then combine the results together as per normal. Okay, so that's we've also got non-linear materials. Now, for a non-linear material, basically we want to induce plastic hinges and that sort of thing in the model. So here we have a simple 2-span beam with a UDL on it, and if we set up some use-defined materials, we can now, well, in the previous version of GSA, you could specify plastic capacities of materials. Now we've actually got a number of different materials types in here: elastic plastic, and also now orthotropic materials. So for your 2D elements and timber materials and so on. We'll be talking more about that in the next webinar. For the moment, I'll just look at plastic materials. So if I base this, let's say, on steel, and we see we've got a yield stress in there of 275 newtons per millimeter. And make sure we apply this into the sections. Now, if we run a linear analysis on this, which if we just hit the Analyze button, we can see that we get more hogging moment than sagging moment, and that's all to be expected. Now, if we run a non-linear analysis on this with the non-linear materials, what we can do is we can increment the loads until the plastic hinges form. And if I take, oh, I've got the node number 5. Non-linear static, increment the loads, deflection control on node 5. We can make the analysis stop once the model has deformed too far. Being the non-linear, if the model is fully yielded, it will stop anyway, but I'm adding that in just to make sure. And then of course in the Z direction, we add in our low case and analyze and see what happens. Okay. Now that just reached the deflection limit. Alright, I am going to rerun that. And let's just take the displacement control off and see what happens. That's better. We can see here that the sagging and hogging moments are now effectively the same. We've got plastic hinges, and we can see in the loading increments back here, first elements 4 and 5, this is the central parts, have yielded and bending, and then finally the middle 2 spans have yielded. So now you'll note that while non-linear elements automatically cause a non-linear type of analysis, though admittedly it's still it's a linear iterative analysis, strictly speaking. If you have non-linear materials, you need to specify a non-linear analysis to get the plastic hinges forming. Now this load increments is also quite good for geometric non-linearity. So if I take this model, snap through, here we have an arch model. It is pinned at the bottom, and I have a load over part of the structure. And what I'm going to do now is, just delete that, I am going to do a non-linear analysis. Oh, let me just check the, non-linear analysis, incrementing the loads, and I'm going to deflection control on node 8 and the translation of a meter. So basically I want this arch to snap through to the far side. Add in that low case. We won't need a deformation magnification on this. Let's analyze that. And you can see the load factor is increasing, and you'll see it will start to give in a moment. Yeah, we see we're beginning and you see it is now snapped through. It's just a magnification of 1. So this is the actual shape, and we'll see that it snapped through at a load factor of about 4.3. Now you also notice on the readout, if you do this, you get a message saying the load capacity of the structure may be evaluated by plotting the load factor displacement curve. Now you can find this in the chart views. So let's look at this analysis, and we'll see that the as the load factor, as load increased, it reached a factor of about 4.3 before the snap through occurred. Now, if these loads are working loads, that means you're working as a factor of safety of about 4.3. If this was unit loads, then that would be sort of your load capacity. There are different ways of looking at this analysis can be used for not just sort of arches, but sort of general structures where you have got compressions. Imagine sort of bridge trusses and that sort of structure where you're dealing with quite high compression loads and you're worried about stability of it. So that's the various nonlinear aspects. Now we come on to dynamic analyses. So I take another model I've prepared earlier, and this is a simple multi-story structure with floors and a bit of setbacks and so on. And if we can do some various analyses on this of the dynamic type. Now we have 4 dynamic analyses in GSA. We have the modal and we have the RITS. Modal looks at vibrations in all directions. RITS is usually used for seismic analysis, and it concentrates the analyses in particular directions. We also have P delta aspects to these analyses. What this does is it takes into account the axial load on the various elements and see how that affects the vibration. Now imagine, as you will, when something is in compression, its stiffness is reduced and therefore it vibrates at a lower frequency. Conversely, if it's in tension, imagine sort of a guitar string or something like that, then the frequency goes up because it's then stiffer. So let's run a modal analysis, and we can choose a number of modes to look at. We can add in additional restraints, but we don't need to in this model. We can say force it to vibrate horizontally or vertically. We can, if we're looking for vibrations up to a particular frequency, we can have cutoffs. The mass is included. This is self-weight calculation, so we do not need self-weight from the loads, but we can generate mass on the structure from the applied loads. I'll just take 10% of the live load for this, and we analyze. Right, that's done. And let's look at some of the results. So the first vibration mode is just over half a hertz, and so on, and we'll get a number of other vibration shapes. Now we can look at these in summary. If I go to the output and get the global dynamic summary results, and we can see we've got the frequencies running from half up to about 5 in this particular analysis. Now that's important for the seismic people. You see we've got the accumulated mass and the number of modes coming in here. If we similarly run a RITS analysis and just ask for 5 modes in the 2 horizontal directions, and again add in some dead and live load, Run that. Okay. We can see that with the Ritz analysis, it it actually gets over 90% accumulated mass, in least in the y direction there, within just 3 modes rather than 4. The bigger the building, the more pronounced that this effect will be. Right, let's erase those results, and I am now going to do a Ritz P delta. Now the basically for both modal and the Ritz P delta, we add on an additional P delta case. So let's just take 5 in each direction, add in my dead and alive, and I'm just going to copy those down into the P delta. So this will load up the structure, reduce the stiffness in the columns, and then give us results. And so you'll find that the frequencies will be slightly lower in the structure. Again, the bigger the structure, the more pronounced the P delta effects will be. And there we have our modes. So there, yeah, not a big difference in this particular example. Now, once we have the Ritz analysis, what we can then do as a post-processor on this is to examine the building under seismic loads. Now, what you need to do for the seismic is to specify a response spectra. If we look at, we have a number of code-based seismic checks, and you can define your own as well. This then deals with all the various aspects you need to set for the seismic, and the properties, damping, and the response curves. We also need, once we have that spectrum, to say we want the response to be plotted in particular directions. In this case, the x and y direction, and you can choose a CQC or SRSS summation of the values. So let's run a new analysis. Because we've now got dynamic results, these dynamic responses are now available to us. So response spectrum, choosing the last Ritz analysis, because the other ones haven't got results. Let's analyze this. Right, that's complete. So what we now get, if I set, we can set get the bending moments from the responses. We can get the axial loads, and so on. Or of course, if we go to the output, what we can do is we can say, okay, I want the beam forces and moments by property, give me the summary, and I want so it's A36, A37. So this will give us the worst results of both. So we can see for the column, for example, we can see the maximum axials and moments and so on, and the beams in one direction, the beam, and all the various elements. So you can use these for your worst case design criteria. So that's response spectrum. Now we can also do linear time histories with GSA. So if I take another model. Now this is a model of a building stability core, and because the rest of the structure doesn't contribute to the stiffness, the stability is just provided by the core. In this model it's been simplified so each floor is represented by a mass, which clutters things up a bit. So I'm just going to switch those masses off so we can see the structure. Now what we need to do for a time history is again run a dynamic analysis on this first of all. So I'm just going to run a modal analysis and just take well, you have to run sufficient modes. I should take 15 off here. I haven't got any additional forces to generate loads. So let's analyze that. And we can see from this vibration we get a number of vibration modes. Now what we want to do now is do a time history of the effects of a wind gust. Well, it might be a wind gust, it might be an explosion, it might be some other transient loads on the structure which is such a short duration the structure hasn't had a chance to fully respond to it. Now for this we will need, under dynamic response, a load curve. If I just delete off this load curve, these load curves can be a seismic one, such as if I look at the wizard on this one. They can be quite complex, or in this case I'm going to do as a wind load gust of just a 3 second gust. So at 0 times 0, at 1 second it's at full value, at 4 seconds it's still at full value, and at 5 seconds it's dropped back down to 0 again. So it's a very, very short gust on this structure. I'll then do a new analysis on this time a linear time history, where I take the modal results, I say I'm using the wind load, and the curve is the wind load curve, set the damping value for the overall structure, and also look at how long we're interested in the structure. Now it was a 3 second gust, so if I take it up to say 6 seconds, so the wind has actually dropped off by this point, and time interval. And what this has done has given us the time response, or the response over a number of seconds. So if I look at, say, how the wind load is gradually, and it's bounce back the other way. Now, as obviously these are moments all the way along, so let me generate an envelope on these. So if I do an envelope of these time histories, I can then get out the bending moments on the structure, and also the strings, the displacement on the structure. Basically, so this tower is actually deflected over about 2 meters under that gust, and of course you can get the output, the bending moments and forces and so on for your detailed design. Now, 2 more types of analysis we can do is the footfall and the harmonic analysis. These are similar in some respects, in that they are regular vibrations being applied to the structure. Footfall is a human-induced vibration, people walking around, and the harmonic is from vibrating machinery, plants, compressors, washing machines, that sort of thing. So, first of all, I've taken a subframe from the multi-story building we looked at earlier. Because this is a low amplitude vibration, we're allowed to take the cladding restraining the floor edge. The columns are all half height with pins at the end, and we have the loads on the floor. So first of all, we need to do a modal analysis on this floor, and I'm just giving a number of modes. You need to get modes up to sufficient frequency. I will include in here dead and live loads on here. Alright, that's done. And let's look at the results. Right. So the first vibration mode, it's looking quite good. Yep, shaking nicely. And sometimes the contour results can help. So if we look at the 2D contours, so we can see the vibration shape, and similarly we get the other vibrations, mostly in the large central part, and then eventually, yes, there we go, we get vibrations, like localized vibrations begin to occur in those wing areas. Now once we have the sufficient vibration checks on here, we can then run a footfall analysis to look at how the floor vibrates under people walking around. Now footfall is sort of a whole webinar in itself, so we'll plan to have a good session looking at this later in the year. But for the moment, just say you can analyze the floor to using the Arup concrete center methods, the SCI methods, and the AISC methods. Right, we get the footfall results, and we see we're getting various responses over the floor, concentrated in certain respects in these edge areas, also in the middle of these long spans. Now I mentioned earlier about machinery loads, compressors and that sort of thing. If we wanting to model these sources of vibration, what we need to do is put point loads into the structure, and these point loads need to be equal to the weight of the machinery. And this is a 10 kilonewton piece of kit, and likewise I've got another over there. Now the eagle eyes will notice these are probably quite bad places to put the vibration machine, because these are on the vibration sweet spots, but it makes some better pictures and illustrates the point. So let me do some harmonic analyses on these two compressor locations. Now again, we take the existing vibration analysis. We say, okay, I want compressor 1, and this compressor is going to be vibrating between on a range of frequencies, let's say from 1 to 30 Hertz. And for the sake of the demonstration, I'm going to have the increments reasonably wide. I mean, in reality, you probably want the increments much smaller than this to get the full picture. And the floor damping. And I won't analyze that for the moment, because I'll set up my second analysis at the same time. So this time, taking the second compressor. And again, it was 1 to 30 at 1 Hertz increments, and a 3% damping. So let's analyze these two now and see the results we get. Right, and you see, like time history, we get responses over a range of frequencies. So if we take the first compressor and switch on, let's say, the accelerations on the floor, and you can see the as the frequencies hit resonances with the floors, we get some various reactions over the floor. So what we need to do now is do an envelope of those. So we do and take an envelope of the first set of harmonic results, and while I'm at it, I'll take an envelope of the second one as well, so we can directly compare. Okay, so enveloping the results. The first compressor which remember is over here, we can see we're getting a acceleration on the floor of 3.5 meters per second in this area, but we're also getting vibrations over the whole floor as well. So this piece of kit is affecting just about the entire floor. Conversely, if we have the compressor over in this corner area here, we're getting much higher vibrations on the floor locally to the compressor, but the rest of the structure is virtually unaffected. It's very much a localized problem. So you can use this to actually examine good places to put the plant, or alternatively the effects that plant will have on your structure. Okay, so that's look at vibration. Now then, what about buckling? Have people used GSA for buckling checks so far? Good, coming in. Buckling looking reasonable. Okay, right. Let's have a look at these results. Okay, you can see, okay, just over half of you have used buckling. Interesting, but just under half haven't. So let's look at the buckling options. So there are two types of buckling in GSA. We call them member and the modal buckling. Let me take this little example first. This is a column subframe. You can do this on a full-size model, but I'm using the subframe, and it has a point load at the top, and this point load is just a unit value. And at half height, I've got a minor axis restraint on this column. Now, if we can use the non-linear member buckling to see how this column will actually deflect under load, and the elements are elements 1 and 2. So let me run a new analysis task, which is going to be a member buckling check. And what this will do is it will iterate, it will increment the loads up until it fails. So we're interested in elements 1 and 2. That's ones we're looking at. We add in our unit load, and it's going to magnify the deformation. So let's analyze this and see what happens. So loads are increasing, and it says it's finished. So again, it's look at the curve, the chart to the values. So this chart, if we look at the not scale it. So this column has buckles, and again, if we look at the chart view for this, we can see that as the load increases, the deflection, it begins to buckle out, and then it goes. And so you can make a judgment on what axial load you're happy with that column taking. Now note that this does take into account non-linear materials as well. Now there is another option on the buckling checks, which is the modal buckling. And the modal buckling looks at the different ways this column might bend. Now in this, I deliberately had a restraint on the minor axis. So usually when you design a column, you've got to check in the two directions. So let's do a modal analysis, the modal buckling check. For the first two modes, I'm going to have in my unit load in there, and I'm also, to avoid torsional instabilities, I'm just going to suppress the torsion in this model. So we now have two modes, and we see the first mode where it's buckling in the major axis direction. We've got a load factor of 650, and which essentially is the actual capacity of that column in the system. The second mode, we see we've now got a minor axis bending, and we've got a load capacity of 1165. So this was a unit load. Alternatively, if we're using working loads, then this would be the factor of safety on that structure. Now this modal buckling can be used for other types of buckling checks, such as lateral torsional buckling. Now this is a plate girder that I've made out of 2D elements. And you can see we've got supports at each end. I've also included a UDL on the top flange, and this is sort of a working load on this girder. Now, to compare the results with and without the stiffener, I have set up an analysis stage, and we've got a stage which says no stiffeners, and it's everything except property area 4. Property area 4, of course, is these purple elements, which are the stiffened elements. So let's set up my two analyses. So the first one is again modal buckling on the whole structure. Just get the first mode and have that top flange load there. Let's not analyse it yet, because I'm just going to add in the second analysis, again modal, this time with no stiffeners. Again, first mode, load case 2, and analyse both of those. Wait for a moment, and they're done. So the results: mode 1, we see the plate girder is. Oh, let me switch off the initial state so you can see a bit clearer. You see this plate girder is buckling laterally at a load factor of 2.7, which is quite comfortable. Whereas if we go to the second mode, oh, we're now getting need to be told that we should be using the different stage. So this is the buckling without the stiffeners, and you see this load factor is coming in at 1.3, which is still safe, but it's sort of getting within limits of factors of safety. So we might need to reconsider this particular option. So you can use the modal buckling check to actually work out the structural capacity of your elements, or even of the structure as a whole.